Hi, welcome to Module 5. This is a final module of this course and we are going to take a bird's eye view recap of everything that we did so far, specifically in the perspective of the field, which will give us a good segue to talk a bit more about state of art of machine learning tuning nowadays and what are the outstanding challenges in the field. So we will have 3 parts today: recap, then state of art of machine learning tuning, and towards the end I am going to advertise an optional machine learning project that we can help you supervise via the course forum for those of you who subscribed. So let's start with the recap. Over the last 4 weeks, you saw 4 albeit basic but super relevant examples of the role machine learning plays in tuning at the level that you can easily run it on Google Colab, but also related to the actual experiments and the ways labs around the world are using machine learning for tuning nowadays. We covered machine learning for quantum dot configuration. Then we created a slightly more challenging scenario by calibrating a charge states, by embedding a neural network into the feedback loop. In Module 3, we looked at some examples of unsupervised learning, and in Module 4, we discussed fine-tuning, all the different flavors it can have, and we gave these very specific examples of compensating for Overhauser field effects. So now you saw examples that you can have machine learning algorithm for pretty much every stage of tuning, from a really coarse tuning to a fine tuning to maintain your experiment in the operating regime when you want it to have. So now the natural question to ask is whether you should use them, how often and to which degree, and should they even be replacing standard algorithmic routines. So this is of course a legitimate question, so let's look into it in a little bit more detail. This is also a slide you saw in the other course in a Quantum 301 program, and I was talking about it there for quite a long time. But let me just quickly recall this, because there is this really essential difference between traditional programming and machine learning. It's also important not to think about it in a completely binary terms, because as the programming techniques keep developing, this difference is becoming less and less pronounced and they are becoming intertwined with each other more and more. But for the purposes of our discussion today, you can think about traditional programming as something that gets an input and the program that you wrote. It can be a for loop running for all the instances of the array and returning you some value of the function that you wish to evaluate on that data, right? That's a great example of a simple program. And when you run it, you are going to get a result. In a machine learning, at least in the framework that we were discussing within this course, what you get is an input and a desired result. You get a charge stability diagram and a label, whether it's in a double dot or a single dot regime. And what you get out is the program, because, for example, your neural network adjusted all of its weights and biases to approximate the function to the highest possible degree that maps your input on the desired result that you gave it. So, of course, it doesn't make sense to train a neural network if you just want to assign a function value to the fixed function value to the assigned item in an array, right? You know easily how to do that. But there is a lot of instances where you don't have that underlying function. There is some physics going on that is pretty complicated, and therefore writing a sort of fixed traditional program is not an optimal solution. For example, the charge stability diagram for a same system can really vary if you measure it a few times, just because of all of these emergent interactions that we were discussing that just happens in a solid state system. So do you wanna, with a fixed programming, account for all of these options, or do you just want to have a more flexible program that will learn from all the possible instances of your data and sort of determines the most general function that will be most successful in a large number of cases? So when you take into account the challenges with quantum control in this inherently noisy solid-state situations, it's actually pretty reasonable to think that there will be a lot of cases where you need a machine learning, but there will also be a lot of cases when you don't. So where we are now is that what we always want from tuning is to develop universal, scalable, and not device-specific methods, right? We want to have, whether it's a machine learning or not, some kind of robust algorithm that is going to do a good job no matter what kind of mood your experiment is on a given day. You just have a goal to get this tuned and you want to do it quickly, efficiently, and robustly, and you don't want to rewrite your whole algorithm every time you change the design of your device just slightly or anything like that. So there is a lot to do with a traditional programming because in a lot of situations the measurement features are just robust and they are not going to be affected by the noise to the degree that, you know, doing this whole machine learning machinery would be justified. But at the same time, there are clear boundaries, especially when tuning really larger scale devices. The number of parameters that you need to have a control over becomes really, really difficult. So in that sense, it's sort of reasonable to assume that machine learning will be better at generalization. There were a few first examples where for a sort of larger number of parameters, machine learning is giving a nice results. At the same time, it's a super developing field still. You saw that the papers we cite or give you to read, they sort of start in 2019. We had some super nice successes on a smaller devices, but there are still things that needs to be demonstrated and resolved even in a machine learning scenario. Okay.